centrality. All right. So, of course, a social network is represented by relations which are captured by a graph. So we introduce the notion of social graph, which is a mapping, of all the nodes in the network, right? And it records the relationships. In particular, looking at a contact graph, which stores contacts among the mobile nodes. And this contact graph is constructed as we go. So this is constructed in distributed fashion. So the vertices here represent mobile nodes. It could be people, pedestrians, it could be cars, it could be drones, whatever moves. And the edges represent the fact that these nodes have met in the past. So the contact means that nodes have met in the past and with some frequency, and we'll see the details in a moment. So this is the angle of the way we apply network science in our project. I mean, network science is a way of using social graphs to improve your application, to utility. And in fact, in this case, we use this social network to improve the delivery of messages to the destination. And in fact, at the end, we show that with social graphs, we can do better than just plain operations without knowledge of the connect times. So there are a few concepts that we introduce here in order to set up our algorithm. The first concept is centrality. I think these are concepts which are well known to the audience here. But the centrality is measures the number of shortest paths passing via a certain node. And for instance, in this case, suppose that we have a node U here. We have sort of two communities which are connected by this stretch of nodes. Imagine now that all the nodes are moving and they happen to be in this position at some time. So node U has to transmit a message to node B down here, and it has to decide whether, now U is in contact with a number of nodes, it has to choose the best next node to transmit the packet. In this particular case, the network is connected, but of course you can imagine this will work also if there is a disconnection here. So U checks its contact with A, and in fact they exchange information and discover that A is better as a higher centrality to V than itself. In fact, if you compute the number of paths that connect this community to V, clearly A has more paths going through than U, so the passage is passed to A. A is higher centrality. Okay? All right. So that's the way the selective forwarding is done on the basis of social networking. The social networking will be able to recommend a node which is more connected to the destination because there are more paths to the destination than you have. So another concept that we introduce here is social tie. Well, actually I realized, sorry here because, well, maybe I should switch to my own laptop then. I realized the equations do not come out properly. I should have expected that. But let me just do one quick thing here.
Could you change the source?
Huh? No, because actually...
No, could you change the source?
Oh, it's already perfect, Um, it's okay. It took a bit of. So I'm sorry for this intermission, but I think it may be easier to look at these slides than trying to explain what was going on. Actually, it's easier for me too because I cannot quite see that slide, that screen, and that one. I have to twist my neck, but anyway. So the social tie describes an impersonal, interpersonal connection by way of friendship or acquaintance. And the strength indicator of a tie is the frequency and recency of encounters. So this is a formula used. Suppose that you want to find the social tie between the social tie of node I with node J. So you have to figure out when node I encounter node J, so maybe they encounter Tij way in the past, and the K is the K time they encounter. So T is the current time minus the encounter time. And so you have a function which is a decay function. You end up all these encounters, and that will be your social tie. So basically, the social tie tells us, social tie of this node to another node tells us how often we met the node in the past, and the expectation is that the meetings in the past are representative of what will happen in the future, right? So if you want to go to a certain destination, you would choose a node with a strong social tie to that destination. So select a relay with a stronger social tie to destination than you, for example. That would be a good criterion to move on with that. Okay, so this was the background of about the social network information we will be using to do our routing. And we wrote a paper, published in Infocom a couple of years ago. And this paper is about information-centric, delay-tolerant, opportunistic managed routing. So it's a mouthful, but what that means is that we will deliver data to based on content criteria, and I'll explain what that is all about. So again, the motivation is that we have networks that sometimes are disconnected. So this is a picture of a planet where there are communication between vehicles, communication from vehicle to the infrastructure, and also exchanges within the backbone itself. But at night, say, you can't be guaranteed that there will be a connection to the infrastructure all the time. And also, some cases when there is an emergency, the infrastructure will be wiped out, like earthquake or floods and so on. And so we really have to operate in a delay-tolerant mode. Delay-tolerant means that our communications can tolerate delays up to maybe minutes before the data is delivered. So the question again is, how do we use... so let me just make a point here. If the network is connected, then the way we will route in the network is via shortest paths. And there are very efficient algorithms to maintain the information throughout the network. So that's done easy, it's just a matter of efficiency. If the network is disconnected, and then if you try to use the conventional routing mechanism, that will fail because at some point you get to a node that doesn't have a connectivity to the destination, so the message is dropped. So that's where you must use this opportunistic network. So the focus of the paper, and moreover, we are assuming that we are not delivering to a particular destination, rather we are looking for content. So for instance, you're looking for content like what is the best way out of this position I am, or where is an ambulance, or where is information that I need in this particular application. So this content-based routing has become very popular because you can imagine in a very large vehicular network, you're not really trying to reach a particular driver, typically try to reach information. So content is the goal of this operation, and we'll build it into our algorithm. And the proposed solution is a social type-based retrieval. In fact, the algorithm that we'll be using is called social type content routing, STCR. And this algorithm brings together the DTM mobility awareness and the content retrieval concept. Now, this picture gives a preview of how the method will work. And so let me see if I can go through the various steps here. Here is your manet. The blue nodes are the mobile nodes. And this actually, I'm not sure that you can see the details of this picture. I have to apologize, but I have bigger pictures later on. So, but the first phase is that nodes with content broadcast their information, and in fact, instead of broadcasting to all the nodes within the manet, they push it up to nodes of higher centrality. So the centrality is a key concept here. The centrality is extracted by the social network. So as I meet neighbors, I inquire about their centrality, and I will advertise the content that I have along the path of increased centrality. So you can imagine if you have a network, so taxi cabs, and most of the taxi cabs gravitate around the train station. So eventually, my messages, my advertisements will go up to this hotspot. Then one of the, say, taxi cabs, if you're using that application, will send an interest packet, and the interest packet also follows the path of increasing centrality. So eventually, the interest will meet the advertisement at the same place. The advertisement carries the location of the content. So at this point, the two nodes, the information of request for this content and the advertisement meet. So the request message is routed to the content using social network, and we'll say, using in this case, we just progressively move the packet towards nodes which have better reachability to the destination, and then once we reach it, once the content is reached, then the content is delivered to the requester. So we have a triangular operation here. And all this is managed through the social network. Now, this is different from what you would do in a typical content-centric network, because typically, if there is no structure here, you broadcast the request to the entire manet. So if you have maybe hundreds or thousands of taxi cabs, it floods the entire network. Once you eventually reach a content, then the content will come back to the requester using what we call breadcrumbs. So you create a path to the destination, and then the data comes back to the source. So you see that the brute force method is much less efficient, and it creates much more overhead. So this method that uses social networking is clearly more efficient. Of course, it requires also more overhead. So these are the things we have to look at. So I think I gave you an idea of how we now use the social networking information for improved routing. So the paper is quite technical, but I hope I can go through some of the, I will not go into much detail. Now here, well, the social tie concept, I already introduced it before. So the social tie is the social relationship of a node I to node j, right? And it is based on frequency and freshness of encounters. And again, the function here keeps track of all the past encounters and discounts them exponentially based on time. And we want to point out that this mechanism of exponential discount is good because we don't have to keep track of all the encounters, you know, so we have just a sort of limited amount of information I have to keep per destination node, right? So reduce computational and storage overhead. Then we use the encounters to compute centrality. So the centrality now is defined as the average social affinity with all other nodes from node I. So the affinity is based on average social type values, low skews, added up over all the nodes. So a node centrality is computed by taking the social ties of node I, say, to all the other nodes in the network, right, and averaged out, normalized by n, multiplied by the factor alpha. And also, what I want to make sure is the centrality is not just reflecting the fact that this node talks to a buddy all the time, they're always driving together. I want to make sure that it reflects the social ties over the entire set of the mobiles. And so I use this function, which is known as the James index, which is maximized when the social ties are distributed to all the nodes in the community. So if I only connect to one neighbor, this becomes 0. So, okay, these two important components are then combining the linear combination here. So the more central node is node that maximizes this function. And notice that so the centrality is computed by each node as it travels through this community. So say taxi cab drives, and as it moves around, it gets in touch with other nodes, so it can compute its social ties to other nodes, and eventually it computes the centrality. So the centrality is the most important parameter here. So each node is computed, and then when they meet, they exchange it with each other. In fact, each node independently, as it meets other nodes, learns about their centrality, and it organizes the centrality of the nodes that it has met so far it classifies them based on the clustering scheme. So it creates, say, k buckets, you know, and it classifies the nodes so far encountered in these buckets using the k-means clustering mechanism. So each node now in its memory will have a view of the centrality of the other nodes in the network. So, so suppose now that node A and node C encounter each other. Node A has a message to deliver to a destination, or it has, so actually node A carries two types of messages. Either it carries a request for data, or it carries an advertisement. So, and we explained before that the idea is to dispatch this message to nodes with high centrality. So, the question is C belonging to my cluster? If so, do nothing else, keep moving. So, we use basically these clusters to reduce the overhead, otherwise you take baby steps to go to the top, transmit it to nodes with just incrementally better centrality. We want to take bigger steps. So if node C belongs to a different cluster, then of course you forward the message to your message to this node. So, and this is a picture that explains sort of the rationale for it. You have node A and node C. You see here node C has passed to more nodes, so clearly node C pictorically has higher centrality than node A, which only talks to a neighbor. So A will pass on the message to node C. And actually, this is sort of completes the most important, interesting part of the schemes, because so we talked about the way interests are being propagated upwards. The advertisements are propagated using Bloom filters. So a node, suppose a node has a certain number of content files that it wants to advertise, maybe 100 content files. Instead of sending 100 files, of course, you would compress them in a Bloom filter, and the Bloom filter then is moved up, again using the scheme that we described before, from one node to the next, following this centrality mechanism. So each node epidemically propagates its Bloom filter digest upwards in the cluster hierarchy. And the top of the cluster hierarchy, Bloom filter digests are replicated across the cluster. We do that to speed up the matching, because as you see, the interests are also propagated upwards, so the place where they meet will be the top centrality cluster. And so the replication of Bloom filters will help the match. Now, suppose that, and of course, the interest constantly looks for nodes which carry the Bloom filter of the content it requires. So the content I require is checked against the Bloom filter. If there is a match, I will look for the ID of the originating node, right? And then I have a problem that I must deliver this interest for it to the node with my content. How do I do it? Or I use social tie routing. So this, when I go downwards, of course, I will not use the centrality criterion, but I have the social tie criterion that tells me which nodes have seen that destination more frequently, right? So there are two concepts that I use from the social network. One is the centrality to go upwards to a meeting place, and the second one is the social tie that takes me to a desired destination. So I follow this brown pointer until I find my desired destination. And remember, this happens while this network is still moving, can be disconnected. There may be no path at any given time that follows the entire path, this set of hops. So I may have to wait and move around until eventually I reach the destination. And here again, the content has to be delivered to the requester, and I use again the social tie. So putting it all together, so this is what we have. Now this seems to be a pretty elaborate scheme, And in fact, actually there are even more elaborate schemes. In this case, I didn't bring in the caching, which can be also included using social networking for efficiency. So I kept it simple. So it's an operation involves the advertising up to the most central area, propagation of interest, and then get to the content, and then deliver the content to the source. And you see that this is a more structured, this type of transmission and search for the content is much more structured than the conventional way of broadcasting the request to the entire network and then following the breadcrumb trail backwards. Right. So, in fact, we're interested in the performance of the scheme, you know. And as I mentioned yesterday, one of the problems is to find good traces, good experimental scenarios. But fortunately, some researchers in this area have taken advantage of conferences to turn on the Bluetooth connection in the smartphones of some of the attendees. So the attendees for the 3 or 4 days of the conference were running around with their Bluetooth connectivity turned on, the radios turned on. So they recorded the contacts, and we were able then to regenerate the traces. So we've been using the trace collected at Infocom in 2006. And there was 98 nodes monitored for 95 hours. So we take these traces, which are implemented in the simulation, NS3 simulation, and every 30 seconds, a mobile generates an interest from one random file. So we assume that each node has a distinct file. So again, the problem is simplified because in general, each node has a multiplicity of files, and that's what justifies the use of the Bloom filter. And in fact, actually, I should say another thing, is that since there is only one file per destination, so the problem of content searching is equivalent to the problem of conventional routing. You know, when you want to route to a particular file, you actually route to a particular destination. Also, for simplicity in our application, we do not cache content. We just keep a single copy of the content with the original node. So we run the experiment every 30 seconds, one request sent out. We set the time to live in the simulator, so after 4 hours, the whole thing stops. So we collect 4 hours worth of data. And the metrics that we use to evaluate our scheme against other schemes are the hit rate, so what is the probability that we get to the file. The probability may not be 1, because the nodes may actually never meet each other, even during the experimental period. Measure average delay and total cost in terms of overhead. These are the typical performance measures that one uses. So compare them a second. We compare the social tie content routing, that's the way we call our schemes, with three other schemes that were proposed for this type of operation. So epidemic is the basic schemes, the one that does the broadcast. Actually, it's a modified scheme because we broadcast interests from the requesters. Also, we broadcast Bloom filter tables from the content owners. And when the interest meets the content, then there is a propagation of the content back to the request contact recency, and without also the notion of fairness, like James fairness. People rank is even a simpler scheme because it doesn't use the concept of hierarchy. It just propagates to nodes with higher rank, so nodes with higher connectivity, which is intuitively good thing to do because as nodes with higher connectivity are the ones that are probably closer to the hotspots. All right, so, and the question is, how do we compare to these schemes? So the first diagram that I'm showing here, I hope you can see this one, plots the hit rate as a function of time to live. So as you stretch the time to live, eventually in 4 days, most of the requests will be satisfied, assuming that the user kept their radius on all the time. But imagine, this is a conference, so there is a probability that two users may never meet each other because they go to different sessions, and one maybe leaves the phone in the hotel room and whatever. I didn't really know exactly how they behave, but in this case, you see that as you increase the time to live, that is the time for the nodes to meet, eventually you reach a very high hit ratio. I mean, the most is 80%. And interesting enough, if you look at the best performance, here is the epidemic mechanism. So epidemic is really the best of all worlds because you try all the possible paths, you know. So you try all the paths and epidemic wins. However, the second best is this social tie content dribble routing. And it does better than bubble wrap and people rank. I mean, it doesn't do superbly better, but it does better. So that's usually what counts in this type of work. And it does better because it uses more information. Also notice that this method is delay tolerant, as you expect, because how frequently can people meet each other? 90 people, a conference with, say, 1,000 people, the probability of meeting within Bluetooth contact range is not that great. At that time, Bluetooth had the range of maybe 10 meters, so that could be really close. But eventually, you know, as you build up to let's say, one day, you get most of the performance gains achieved. So you say, okay, so far we see the epidemic is the best. So you say, why bother with social network? Okay, let's see a second measure. The second measure is average delay. Average delay means that we try to reach a destination as fast as we can. The delay in minutes, of course, will be proportional to the, so as you increase the time to live, the delay will increase because more and more data will be delivered, but of course the delay will increase. Now, interesting enough, the scheme with the lowest delay is again epidemic. Not a surprise, because the epidemic will choose all the possible paths, and eventually the epidemically transmitted packet will get there first. So we say, well, at this point we lose, and well, STCR is the second best. We say, well, then why bother again with STCR? So epidemic is the best. Well, the third measure is the one that has to be shown to complete the picture, because epidemic, okay, there is an issue of overhead. Epidemic broadcasts, and so that cost must be accounted for. And it is accounted for in the total cost in terms of packets transmitted. And you see that the epidemic scheme now has a cost which is twice as much the other schemes. The lowest cost is the cost of the social tie scheme. So basically in this competition, social tie wins big over epidemic in terms of overhead, and eventually overhead is one of the most important measures, because if you increase the network size, then the broadcast will eventually kill you. We didn't do this study for the scalability study, but it's clear that epidemic eventually will just not deliver anymore because the network will be congested. Okay, so this was a pleasing result because it shows how social networking can help in our situation. So I'm ready to summarize here. So we have been using social networking to improve the chance of delivering packets in an opportunistic manner, and we select the relay nodes based on the social characteristics. Now, this centrality and the other parameters have been computed completely in a distributed fashion, and that's important to bring up because one of the issues in these systems is privacy. So if you take the information and pump it up to a central controller, and then the central controller decides which are the best paths to route on, you have a privacy issue. And in fact, in some cases, these networks are run because you want to avoid the control central authority. So in this case, since the scheme is totally distributed, there is absolute privacy. I mean, there is no loss of privacy because what the other nodes see is what they would see even without the social network built in. So it's a good way to handle privacy, to use this distributed solution. Now, of course, social studies, the social parameters can be used also beyond routing. In fact, we published a paper just the following year explaining how social networks can be used for cooperative caching. Now, caching is important in content delivery networks because caching improves the chances of getting the data. So you can use social networks to improve that as well. Future work. Well, there is more work in the direction of fairness and load balance when you choose relays. We didn't look at that because the network is very lightly loaded. If you increase the load, that will be a factor. You can also extend it to hybrid systems. For instance, you may have a combination of vehicles, pedestrians, in some cases they interact with each other. Maybe now drones, popular. So I think in the future, and these are mobile networks which cannot be guaranteed to be connected all the time, so that will happen. There is also an interesting issue here of possibly combining centralized and distributed social network maintenance, because some of the nodes may be connected to the network all the time. If there is no privacy issue, the centralized scheme, of course, that's better. And then some other nodes are disconnected. So there are still directions for research. Now, I would say at this point, just as a disclaimer, in the sense that this is not the only type of social network we're looking at. We are now looking, as I mentioned yesterday, at social networks that emerge, rise in other situations like autonomous vehicles, where vehicles talk to each other to find the best path. At the same time, they're connected to internet and they socialize with other cars. I envision the situation where you say you want to go skiing, you just get in the car, and of course you get information. The network tells you which is the best way to go to which resort. At the same time, you hear that friends are going to resort A or B, so you make up your mind combining social networking with navigational networking, and there are opportunities there. Opportunities for the customer, of course, also opportunities for the social network vendors because they try to give you advertising, so that there is almost an unlimited set of possibilities. And so I stop here, and I'd be happy to take questions. Yeah.
Okay, so we have time for a few questions. Yes? So you can go down there.
I have a question about another layer, maybe could be added here, namely the content. So the content here was treated as the one piece of information, data, whatever.
Uniform, flat.
Yeah, flat and fixed, constant. So my question is, what if we would add some dynamics to the content itself? So I think that the content, like in the information networks, could be also flexible. It can change and can consist of many components and evolve over time. So in the parallel process, dynamic process. So what if here we have the dynamics of the people moving or the objects moving, and the content also moves.
I think that's an excellent suggestion. In fact, thank you very much, because you're right. So, say the content may change in time, because you're the editor. I don't care about the content half an hour ago. If I'm looking for congestion in particular, crossing, I will put some constraints. So I'll try to get the most recent content, and so I can discount the content with a social network. That can be factored in. Maybe the importance of the content may be factored in. So the content may be hierarchical. The content, you get a very gross view and then a refined view, and depending on what the social network tells me, I go for one or the other, and I take. So you're right. I can use social networking to drive me to the most appropriate content, as I do use the social network to drive to the most appropriate destination, so it can be combined, yeah.
Okay. So, want to get some more questions? Yes, here. Okay.
Thanks, Mario, for this very interesting talk. Can I get back to your last slide, the summary slide? I may have missed that. You say there's a completely distributed solution in the way search is done for routing. And you say this is privacy preserving, but it's based on this social networking characteristics and all the centrality measures and so on. Are all of these measures distributed in computed distributed fashion?
Actually, thank you for pointing out this is very important. In fact, this is very important, and I apologize for not putting it, because as you do in any distributed scheme, there is a problem of attacks. So somebody, a malicious node, probably referring to this, a malicious node may attack. Of course, in this exchange, we use authentication, so we use PKI. So when I get the message, I make sure that you gave it to me, but this does not prevent the fact that some nodes can be compromised. So, for example, smartphones, somebody come in and steal your smartphone and then play games. It just gives you totally wrong information. So instead of sending your message to the highest centrality node, you send them the other way. So if you compromise a large enough number of phones in our application, you totally kill the performance. The algorithm will just collapse. So, in a sense, we have to protect also from the attackers. And the way you envision you protect yourself from attackers is against using the community. You can use a majority rule. You discover that some nodes give information totally different from the others. You start blacklisting them, and you use the community to do that as well.
Right.
Did I answer your question?
I think partially, and it's very important that we talk about attacker models and that we know what we are protected.
Yeah.
Maybe I should shout. Is that easier?
No, but actually I think that, no, go ahead.
Right. No, I was just wondering, in principle, let's say we do not have compromised nodes. But the values of centrality and things like that, are they also computed in a distributed fashion?
Oh yeah, okay, if that was the question, yes, absolutely, because I compute this and say, as I encounter nodes, every node computes on centrality, because every node knows its social tie to other nodes, and this social, so I get more and more social ties that they improve as I go. In fact, in our scheme, you know, we have the experiment going on for 4 days, and you can guess that it takes probably a good part of the day for a node to meet all the others. So the nodes learn about the social tie to other nodes, they compute their centrality. Each node knows its own centrality, exchanges with the neighbors. So through this exchange, every node now gets the global view of centrality, of course, subject to the encounters. So it's all distributed.
Right. Okay, so it would be super interesting to see what gets leaked under which attacks and under which, let's say, weaknesses of some node being compromised.
You're right. So since you get this global view, you already see there are some outliers, and we really didn't. No, that's a direction that should be definitely explored. People ask me the same question, but we should really look at that and the robustness of the schemes. I think, again, social networking would be helpful to counterattack here.
Okay, some more questions from the audience? Okay, so if we do not have more questions, we have some present to you to acknowledge your excellent talk. Thank you very much.
Thank you.
Okay, so